Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 8th lecture. And last time we were looking at complex value functions and vector value functions, and we saw an example last time, we ended with an example last time, of a complex value function that showed that the mean value theorem did not hold true for complex value functions. Today we want to take a look at the complex value functions, two of them, that showed that L'Hopital's rule doesn't hold true. So here's our example. On the open interval from 0 to 1, we define f of x equaling to x and g of x equaling x plus x squared times e raised to the I over x squared. Okay? And we want to take a look at the limit as x goes to 0 of f of x over g of x, which in this case is going to be equal to x over x plus x squared times e to the I over x squared. And then we can factor out x in the bottom and cancel with x in the top to get 1 over 1 plus x times e raised to the I over x squared. Then, of course, this should have limits out in front of it. So this limit as x goes to 0, and here's then the limit as x goes to 0. Okay, now we want to start with applying here. We're applying that the limit as x goes to 0, really it's 0 from the right, of x times e to the I over x squared, that this is equal to 0. So we're going to work on the proof applying for that. Okay, so here's the proof of the plane. So we're going to let epsilon be greater than 0 be given. We need a delta bigger than 0 such that the x times e to the I over x squared minus 0 in the complex numbers, so this is the distance in complex numbers, is less than epsilon, and this is true for all x element of 0, 1 with 0 less than the absolute value of x minus 0 being less than delta. Okay, well, let's look at what we're trying to make less than epsilon. Note this x times e to the I over x squared minus 0 in the complex norm here is equal to x times e to the I over x squared in the complex norm, which is equal to complex norm of x times the complex norm of e to the I over x squared. But the complex norm of x is a real number, that's nothing more than the absolute value of x in the real number system. And then times, this is going to be the square root of cosine squared of 1 over x squared plus, this is going to be just sine squared of 1 over x squared. And this, of course, is equal to 1. So this is equal to the norm of, or the absolute value of x in the real numbers, which is, of course, equal to the norm of x minus 0 in real numbers. Okay? And that's for all x different from 0. Okay? So we let delta be equal to epsilon, and then when 0 is less than x minus 0 is less than delta, then we have x times e raised to the I over x squared minus 0, and the complex norm is going to be less than epsilon. So what that says then is that the limit as x goes to 0 of x times e to the I over x squared will be equal to 0. And that's the proof of the claim. Okay. Next thing we want to do is note that g prime of x is equal to 1 plus x squared e raised to the I over x squared times minus 2I times x to the minus 3 plus 2x times e to the I over x squared. So here we're using the sum rule and product rule. And this is equal to 1 plus, rewrite this, it's 2x minus 2I over x times e to the I over x squared. Now, what we'll notice is that if you take the g prime of x minus 1, take the complex norm of that, that's going to be the same thing as 2x minus 2I over x, complex metric, and that's true for all x element of 0 to 1. So, using the triangle clause, what we get is that g prime of x, its norm, plus 1 is going to be greater than or equal to g prime of x minus 1's norm, which is equal to 2x minus 2I over x. So what we have then is that the norm, the complex norm of g prime of x, will be greater than or equal to the complex norm of 2x minus 2I over x minus 1. And that's equal to the square root of 4x squared plus 4 over x squared minus 1. And that's going to be greater than or equal to the square root of 4 over x squared minus 1, which is equal to 2 over x minus 1. So from this, we find that the norm of f prime of x over g prime of x, complex plane, is 1 over the norm of g prime of x. This was 1, its derivative, complex plane, which is going to be less than or equal to x over 2 minus x. Just working with this. So our claim from here is that the limit as x goes to 0 of f prime of x over g prime of x, that equals to 0. So we'll do this in the definition way. We'll say let epsilon be greater than 0 be given. What do we need? We need a delta. Greater than 0, such that for all x element of 0 to 1, with 0 is less than x minus 0 is less than delta, this is the real, then f prime of x over g prime of x minus 0 is less than epsilon. Complex. Okay, well, since the limit as x goes to 0 of x over 2 minus x equals to 0, then there does exist a delta greater than 0 such that when 0 is less than x minus 0 is less than delta, then x over 2 minus x minus 0 is going to be less than epsilon. And so for all x element of 0 to 1 with 0 less than x minus 0 less than delta, then that's the value of f prime of x over g prime of x minus 0 will be less than epsilon. This absolute value here is going to be equal to x over 2 minus x, which we know is bigger than this complex norm. Okay. So what we have is that the limit as x goes to 0 of f prime of x over g prime of x equals to 0. But, and I should have said this earlier, from our previous work, the limit as x goes to 0 of f of x over g of x, well, this is going to be equal to 1 over 1. It was equal to 1 over 1 plus x times e to the I over x squared, the limit of that. But the x times e to the I x squared, e to the I over x squared, we showed that that goes to 0, and so here we just get 1 over 1. So what this is an example of where L'Hopital's rule does not apply. Let me write that down. The last thing that's in this chapter 5, is a statement that's kind of a very similar version to the mean value theorem, and for complex value functions. And here's what it says. It says, suppose f bar is a continuous mapping A to B into RK and F bar is differentiable on, here's the open interval from A to B, then there exists an X in the open interval from A to B such that, okay, so it's the absolute value, or the norm, I should say, of F bar evaluated at B minus F bar evaluated at A is less than or equal to B minus A times the norm of F prime evaluated at X. That's the statement. Okay, we need to prove the statement. Here's the proof. We start off by letting Z be equal to F bar evaluated at B minus F bar evaluated at A. And define this function phi of t to be equal to Z bar inner product with F bar of t, and this is defined for all t's in between A and B. Okay, so the first thing to note about phi of t, that phi of t is a real value function, on A to B, and since Z bar is a constant function, so we're thinking of Z bar here acting on A to B, okay, acting on something A to B. It always generates F bar of B minus F bar of A, so that's a constant. So it's a constant function. Again, Z bar is defined from A to B into RK. So since this is a constant function, we think of defining it this way, then it is continuous on it's continuous. Okay. And then what we say is since F bar of t and Z bar are continuous on A to B, then, this is by a previous fact, there's a fact proven last term. That gives us that phi, which is the inner product between these two continuous functions, phi of t is continuous. very similarly, since z bar is a constant function, then z bar is differentiable on the open interval from A to B. And since f bar of t and z bar are differentiable on the open interval from A to B, then z bar dot f bar of t, inner product, is differentiable on open interval from A to B. So when we're talking about this phi of t, what we're finding is that it's continuous on the closed interval and it's differentiable on the open interval, and it's a real value function. So we can apply the mean value here. Let me write that down. So phi of t is continuous on the closed interval from A to B and differentiable on the open interval from A to B and real valued. So applying the mean value here to phi of t, we have, okay, so it will be phi of b minus phi of a will be equal to, let's see, it's b minus a times phi prime of x, okay, which is going to be equal to b minus a, and then phi prime of x is going to be z bar dot f bar prime acting on x, and that's by the product rule for the inner product. And that's true for some x element of A to B. Okay. On the other hand, okay, if we look at phi of b minus phi of a, we find that that's equal to z bar acting on dot inner product with f bar acting on b minus z bar inner product with f bar acting on a, which equals to f bar acting on b minus f bar acting on a. Remember, that's what z is, times the product with f bar acting on b minus f prime acting on b, not f prime, but f bar acting on b, f bar minus f bar acting on a, time, or inner product, with f bar acting on a. Okay. Maybe a little bit more details on what I need to show here. This is a element in RK. And so what it is, it can be written down as F1 of B minus F1 of A. This is K2 pool. F2 of B minus F2 of A, all the way up to Fk of B minus Fk of A, inner product with F bar of B, and then minus, I'll write the rest of it here. Very similarly, it's F1 of B minus F1 of A, F2 of B minus F2 of A, all the way up to Fk of B minus Fk of A, dotted inner product with F bar of A. Here's where I'm using representation for F, having component functions. This is going to be equal to, doing these inner products, we're going to have the sum as I runs from 1 to K of Fi of B minus Fi of A times, this is Fi of B, minus the sum as I runs from 1 to K of Fi of B minus Fi of A times Fi of A, and this ends up being, a sum of Fi of B minus Fi of A, and then here times Fi of B minus Fi of A. And that's just equal to Z bar dotted with Z bar in a product, okay? And that's equal to the norm of Z bar squared in RK. So what we have is that the norm in RK squared of Z bar is equal to B minus A times the norm of Z bar inner product with F bar prime of X. That's in R. Okay, and then this is equal to B minus A times, this is the absolute value of the sum of the Fi of B minus Fi of A times Fi prime of X. This is times. So here we use something we proved last time about complex functions. So using Schwartz inequality, and this is for complex numbers. A1, A2, all the way up to AN, and B1, B2, all the way up to BN. Okay, what it said was that if you take the sum, as J runs from 1 to N, of AJ times BJ squared, that's going to be less than or equal to the sum of the absolute values or the norms of AJ squared, J equaling 1 to N, times the sum as j runs from 1 to n of the bj norms to be squared. So we're going to apply that here. So we have that the z bar squared norm and RK is going to be less than or equal to b minus a times z bar in RK times f bar prime of x in RK. And then dividing by the RK norm of z bar, thus the z bar norm in RK is going to be less than or equal to b minus a times f bar prime of x. And that's in RK. And or finally, this says that absolute value, the RK norm of f bar of b minus f bar of a is going to be less than or equal to b minus a times f bar prime of x. And that's what we're going to show. Remember this, RK norm. That's the proof. And that concludes chapter 5 from our text. And chapter 6 is what we'll start next. Chapter 6 has to do with the Riemann-Stieltjes integral. And we're going to begin this chapter by writing several definitions, lots of lengthy definitions setting up what the Riemann integral is and what the Riemann-Stieltjes integral is. We'll do some examples and facts a little later, but first we'll get set up. So here's a definition. It says let A to B be a given interval. First thing we'll define is something called a partition. Find a partition of A to B, we mean a finite set the points, and so we have x0, x1, x2, all the way up to xn, where here's some of the only stipulations that we have on these numbers, is that A is equal to x sub 0, which is less than or equal to x sub 1, which is less than or equal to x sub 2, which is less than or equal to, all the way up to less than or equal to x sub n minus 1, which is less than or equal to x sub n, which equals to B. Okay. And so we write delta x sub I is equal to x sub I minus x sub I minus 1. These are, the delta x sub I is the difference between consecutive partition points. Okay? We'll do an example of this. So as an example, if we consider the interval -1 to 4, then script P equal to -1, 0, 2, 3, and 4 is a partition of -1 to 4. And delta x sub 1 is equal to 1, this difference. Delta x sub 2 is equal to 2, this difference. Delta x sub 3 is equal to 3 minus 2, which is 1. Finally, delta x sub 4 is equal to 1. That's an example of partition and delta xi's. Now, here's something to recall from the previous term. It's a definition. It says a mapping F going from A to B into R is bounded if there exists a real number m that's greater than 0, such that here the absolute value of f of x will be less than or equal to m. And that's true for all x element of A to B. So that's something that's going to be important for our definition for these intervals. Here's a definition. It says let F go from A to B into R be a bounded function. Okay, so that's what we have, this period. So corresponding to each partition script P on or of A to B, we put capital M sub I to be equal to the sup of the f of x's here for x sub I minus 1 up to x up to x sub I. So we look at these subintervals, if you will, and we find the sup of all the output values over these subintervals. That's the biggest thing. And little m sub I, that's a little m sub I, equal to the infimum of the f of x's, and that's for all the x's in between x sub I minus 1 and x sub I, partition values. And then we define the upper sum with respect to the partition. Let's call it partition script P. To be, okay, so it's U with the partition in F, and it's equal to the sum as I runs from 1 to n of the capital M sub I times the delta x sub I. We got this upper sum. Well, if we got an upper sum, we ought to have a lower sum. Indeed we do. So, and define the lower sum with respect to the partition. Script P as, so L of the partition F equal to the sum as I runs from 1 to n of the little mi times the delta x sub i's. Okay. So the next thing we'll do is make another series of definitions. So we let F going from A to B into R be a bounded function. One, we define the upper Riemann sum over A to B to be equal to, well, it's denoted by the integral from A to B with a superscript bar over the integral of f of x dx, and that's equal to the infimum of all the upper bounds with respect to a partition and a function, and that infimum is done over all partitions. Well, if we have an upper Riemann sum, we ought to have a lower Riemann sum, and we do. Two, we define the lower Riemann sum I'm sorry, not called the lower Riemann sum, it's called lower Riemann integral. I made a mistake. Okay. And before, for the upper Riemann integral, it should be a mistake, and you come back. Not upper Riemann sum, it's upper Riemann interval. Sorry. Let me get this definition, we'll call it quits. Okay, it's a lower Riemann interval as, so here it's from A to B with a subscript bar of f of x dx, and what it's equal to is equal to the supremum of all over all partitions of the lower Riemann sum, the partition there. Okay? Okay. We'll call it quits there, and we'll begin with some more definitions from chapter 6 and in lecture 9. Thank you very much.